Hello, everyone. Welcome and happy Earth Day. My name is Jessica Kennedy, and I'm the educator for adult learning at the St. Louis Art Museum. Thank you so much for joining us for today's Art Speaks program. Before we begin, please familiarize yourself with the Q&A section located on your screen. Feel free to enter your questions at any time during the program, and we will choose a few to answer at the end. Also, there is live auto transcription available for this program. Please click the CC icon to activate or deactivate the subtitles. For today's talk, Missouri Stones in the exhibition Paintings on Stone, we are joined by John Encarnacion, pardon me, Professor of Geology at St. Louis University. Thank you so much for being here today, John.
Hi, Jessica. Thank you for inviting me. Thanks to the St. Louis Art Museum for asking me to speak with everyone. And thank you all for tuning in and having an interest in both science, rocks, and paintings and art. So today I want to share with you a little bit about Missouri's geology and the stones that we have in Missouri that are featured in the exhibition Paintings on Stone. And with that, there we go. Took a while to change the slide. With that, do we use the word stone or rocks? And as a scientist, as geologists, we use the word rock, but it's the same object. It's the same material, same minerals in the object. Stone is usually the term used by people who use rocks for construction, or perhaps using it as a backing for paintings. So it doesn't really matter if you want to use the word stone or rock. I might go back and forth using the two terms. And those geologists who are watching, please don't crucify me for doing so. I used to always say rock, but I started using stone after working with the good people at the Art Museum. Okay, some of the stones or rocks that are featured in the exhibition that one can find in Missouri are shown here. There's quite a bit that you can find in Missouri that you'll find in the exhibition. But I want to focus on just a couple. And you'll find that many of the stones that are in the exhibition that come under different names, like the two examples there in the center, are really just limestones. So when I was asked by the Art Museum to write up the descriptions of all these stones, I was kind of taken aback by the bewildering array of terms used by the stone industry for many rocks that are really the same rock as far as geologists are concerned. So here are two examples. Dendritic stone, which is really just a limestone with these stains or mineral deposits of manganese oxide that kind of look like fossils. They're not fossils, but they're just natural minerals that precipitated on the surface. It's really a limestone. And then below, looking very different, is this stone that has been called red marble, but it's really, again, another limestone that has been colored with some iron oxides. So we're going to be talking a little bit about limestones in Missouri, a rock type that I think everyone in Missouri should know about. And then we'll follow up with this somewhat odd rock that some people might never have heard of before, called a porphyry. Here is one work in the exhibition. It's painted on a limestone. Beautiful painting. It's using some of the natural patterns one sees in the limestone, which are really sort of stains of iron and manganese oxides on the rock. And for those who are from Missouri, from the St. Louis area or elsewhere in Missouri, you're driving along the roads here and you look out the window of your car, which I did yesterday. I just took this picture yesterday on the highway. I said, I think I need a picture of these typical outcrops. So I took this picture and you'll see a lot of these rocks. This was on Highway 270, just near where I live. And most of it is dominated by limestone, or its cousin, something you may hear about, dolostone. They're very similar rocks. Limestone is the original rock, and some of them have been turned to this other type of rock called dolostone, which has a little bit of magnesium. So I'm just going to call them all limestones, and this is a typical scene one might see. Many of the limestones in Missouri are lying flat. You'll see these nice layers. That's because they are sedimentary rocks. They were precipitated, deposited in an ancient ocean, which we'll see in a moment. There are some really cool places in Missouri, kind of rare, where these limestones are not flat lying. Instead, they are tilted, as we see here. The layers are tilted from upper left to lower right. And these are sort of the structures that get me excited. I like it when rocks are deformed. We go out and I have my students measure the orientations of these limestones. Here's another picture from out in West County. I took this picture when I was out on a run. I saw these nice layers, which you see here. And if you ever see a limestone, you should pause like I did, try to get over to the rocks and look closely. And you just might see something really cool and interesting. So let's zoom in on this rock and see what is making the layers in this limestone. So here we are. I came up close, took this picture. And what we see is this limestone, like many other limestones, consists of the remains of marine critters, in this case, corals. So we see these lines, 2 layers of coral fragments. In between are finer bits and pieces of the remains of marine organisms, which is very common in many limestones. So what may have happened here is we had a reef, as shown in the figure in the upper left, a little cartoon I made. There's the coral reef. During storms, when the critters die that make the reef structures, some of the bits and pieces of the reef material may come off and get scattered off to the right here in the photo, in the drawing. And those bits and pieces of corals form these nice layers that we see in the rock outcrop. If you're ever at the art museum, there's a really cool exhibition there, a cool work of art. It's called The Stone Sea, quite appropriate, by the artist Andy Goldsworthy. And he made these cool arches out of these huge blocks of limestone. A wonderful structure that you should see. You'll see it at the lower floor of the art museum down by the cafe if you peer through the windows there. So where do limestones form? As I mentioned, they form in shallow seas, usually warm shallow seas. A place today where limestones are currently forming is in the Bahamas, just off of the southeast coast of Florida, as we see here. The Bahamas is a place with very shallow, warm seas. And there, a lot of these marine critters are quite happy. They're happy in these conditions, and that's where they start to thrive. They build their hard parts, like the corals build their structures, skeletal structures. And when they die, all this material becomes part of limestone over millions of years. So the interesting thing is that the limestones of Missouri tell us that Missouri was once a shallow sea, was covered by shallow sea. And we see that here in this map. The red arrow near the bottom is pointing to the state of Missouri. Those who are from Missouri can recognize the state outline there. So we were just, very close to the equator at the time. The equator in this figure is in an awkward position, and that's simply because North America has rotated after this time. So after these limestones formed millions of years ago, because of continental motions, plate tectonics, North America has rotated to a different position. So where the equator was is at this odd angle today. Zooming in a bit more, we see that Missouri had these nice shallow seas, but in the southeast corner, just about an hour or two south of St. Louis, the sea did not cover that part. So there were older rocks sitting there that the ocean tried to come up upon. The ocean covered the rest of Missouri, but this part, which was slightly above sea level, higher up, was not covered. So down in that area, which we'll see as the St. Francis Mountains area, that was a tropical island. It was a tropical island that existed 500 million years ago here in Missouri. And if you were standing on that tropical island, you'd be surrounded by nice warm waters, pretty much like the Bahamas. So geologists look at the rocks and we produce geologic maps like the one shown here. Lots of pretty colors. Geologic maps fundamentally show the distribution of various rock types. And on this map, what is being shown are rocks of different ages. And most of these are sedimentary rocks. And I think I have indicated that here. So the vast majority of these colors are sedimentary rock, most of them being the limestones we just talked about, with the exception of the red material that the lower arrow is pointing at. This is the St. Francis Mountains area, about an hour to 2 hours south of St. Louis. And those were the rocks that were not entirely covered by the limestones. So what is exposed there are rocks that are much older that made up Missouri before the oceans came in around 500 million years ago. And as you can see, the area that these rocks are exposed in is not a large area. And the states around Missouri and further out do not have exposures of these older rocks like we do in Missouri. And so that's why whenever I'm down there with my own students from St. Louis University, often we'll see other vans hanging out with geologists from other universities from surrounding states and within Missouri. They all converge on for field trips down here in Missouri to check out our cool rocks, these older rocks that are hidden underneath most of these limestones, except for the St. Francis Mountains area. So that's the second rock type I want to talk about that is shown in the exhibition that we have in Missouri. And it's porphyry, which is shown in this painting. It's the speckled rock you see in the background of this gentleman's portrait. What is a porphyry? So the term porphyry, interestingly enough, was given by the Romans to describe this purplish rock that was used in Egypt, and it was considered a royal stone. So purple was the color of royalty. This rock was purple, and so they quarried this rock and used it for monuments, for busts, for various statues, and it had a royal quality to it. So the original name porphyry was coined because of the color. Today, geologists like myself, we learn the term porphyry as undergrads, and we use it simply to describe a igneous rock, a rock that forms from magma, that contains relatively larger crystals, like we see here in this example, the white sort of yellow stained crystals here. They are larger than the surrounding material, which is the purplish stuff that we call the ground mass or the matrix. So as long as you have an igneous rock with crystals that you can see are distinctly larger than the rest of the rock, you could call that rock a porphyry. And we call that texture a porphyritic texture. So how do these porphyries form? It's a really interesting story. So They form in igneous rocks. So all igneous rocks come from the solidification of molten material, which we call magma, molten rock called magma. So here I've created this cartoon. We have a volcano. Volcanoes are being fed by some magma body underneath. We call them magma chambers. And so I've drawn this blob of magma in red, which is our magma chamber. And the magmas often start out, being largely molten. But as they rise through the crust, they're losing heat. These hot magmas enter the cooler part of the earth. They're losing heat. And as they lose heat, they start to crystallize. So we start forming these crystals in the largely liquid magma. More and more crystals may form. And you end up having this material, which is partly liquid, partly solid. So I've drawn the crystals here in white, not a lot of them yet. And the red part is still molten, still liquid. Now what can happen is, if this magma starts rising up, it may erupt from the volcano, forming an ash deposit. It may come out as a lava flow. And in either case, you're going to have this rock that has the larger crystals surrounded in a matrix that was once the liquid, but which has now solidified. And because it doesn't have a lot of time to develop crystals, it might not even develop any crystals at all, and it becomes solid. So it might turn into a glassy material, or it might have crystals that are too fine to see. And in any case, you form a porphyritic texture. Larger crystals that formed earlier, deep in the ground when it was cooling slowly, and then the finer matrix, which forms later when the magma rises up to a much colder region where that liquid doesn't have time to crystallize. So here are two nice examples of porphyries from Missouri. The one on the right we saw earlier, and the one on the left is another example. Nice large crystals. These happen to be crystals of feldspar, and they're in this darker matrix with a lot of it is glassy material, or what was glass, and a lot of tiny, tiny crystals that are microscopic that you can't even see. So the area of the St. Francis Mountains, that part of Missouri that was not covered by the limestones, consists of these igneous rocks, many of which are porphyries. Here's a shot from one of my field trips. Those are my students. They're taking notes. This is an area called the Knoblich Tower area. It's about 5 miles south of Farmington, maybe an hour and a half drive south of St. Louis. Beautiful area. And much of the terrain we see down there in the St. Francis Mountains, of these sort of rolling hills with knobby hills sticking out, a lot of those high points are made of this volcanic rock that are, in many cases, porphyries. So just to remind you, that's the area down here. The lower arrow pointing to the red material, those are the igneous rocks that we see. And it's not just porphyries. So those from Missouri, you might want to know there are other igneous rocks down there as well. And the variety just depends on where the magmas crystallize. So we talked about porphyries. Most of those are volcanic rocks. Volcanic rocks are the ones that erupt at the Earth's surface. But you can also have the magma just staying down deep in the earth and continuing to crystallize down there, forming a rock that is full of crystals you can see. And those rocks are called plutonic. And a good example are granites. Granitic rocks are plutonic rocks. And we do have those in Missouri. So 3 famous sites that a lot of people here in Missouri go to consist of these different igneous rock types. So Elephant Rock, the first red dot up here, it is made of granitic material, beautiful park with these nice, huge, rounded boulders of granite or granitic material. Tomsock Mountain, which is the highest point in Missouri, it is made of volcanic rock. Some of it is porphyry. and down in Johnson's Shut-ins, a place that a lot of people like to spend their time in the summer because they're nice cool waters to hang out in. That is also volcanic rock. So all of these rocks formed a long time ago before the limestones came in, when the ocean partly covered Missouri. So going back to that again, here's our geologic map. And we've talked about the limestones, which occupy most of this blue area that I just colored in. And then we have the igneous rocks, which are peeking through in this, at this area of this red blob. They exist underneath the limestones, but they're covered. So if you drilled into the limestones elsewhere in Missouri, you're eventually going to hit those igneous rocks hiding underneath. Now, one thing that everyone from Missouri should know about, and this is something that the geologists who are listening in should also get excited about and perhaps know about, is the answer to this question. What is the relationship between the porphyries and the limestones? So we talked about that a bit. I said that the igneous rocks, of which the porphyries are part of, they were what Missouri was made of before the oceans came in. So all these old igneous rocks were sitting around. They formed way before, as we'll see in a moment. The oceans came in, covered those old igneous rocks with the limestone. There are sandstones too, and limestones. So that contact, along which the limestones are on top of the igneous rocks, is called the Great Unconformity, this wonderful phrase to describe it. And the Great Unconformity is that contact between the much older rocks underneath and the much younger rocks above. The Great Unconformity exists in many places throughout North America. It goes all the way up into Canada. You will see it in the Grand Canyon. If you see pictures of the Grand Canyon, you can imagine these flat-lying rocks. Those are the rocks deposited, sedimentary rocks deposited on top of the older stuff. If you hike down into the Grand Canyon, you eventually reach the inner gorge of the Grand Canyon, and the rocks in that inner gorge are the older rocks. And as you hike down, you will pass through the Great Unconformity. And this is another reason why many people come to Missouri, geology departments come to Missouri, because we do have the Great Unconformity exposed here. And this one place I take my students to, you would drive by this outcrop and not even notice it if you weren't a geologist. But we stop here, get out, pass through the bushes, and head up to the Great Unconformity. And it's the surface that I've marked with a dashed line here. So below that dashed line are the igneous rocks, of which the porphyries are part. They are about 1.5 billion years old, with a B, billion. And above that surface is sedimentary rock, about 500 million years old. Let's walk over to that outcrop, come up and see what it looks like. There we are. And even if you're not a geologist, you can see that there are two different rock types here. And there again is the Great Unconformity, the dashed line. Below is igneous rock. In this place, it happens to be a granitic rock. And above are sandstones. So you can imagine as the ocean comes in, the first sedimentary rocks that are often deposited are beach sands. So the beach is coming in slowly, coming higher and higher across the continent, depositing sand first, and then as the ocean deepens a bit, the limestones can follow. So it's quite remarkable. The Great Unconformity, where that dashed line is, marks a missing piece of Earth history. And in this case, the amount of time that is missing in the rock record amounts to about 1 billion years, just incredible. So I have my students put their finger right on that surface, and right where they put their finger, that's like a book where you've ripped out 1 billion years of time, pages of Earth time. Okay, this reminds me of an interesting story. So below this surface, you can imagine that dashed line was the surface of the Earth about 500 million years ago. That was the surface. It was above sea level. It was being weathered. And then the ocean came in and covered it. So that dashed line is basically the upper part of a 500 million year old soil. It was weathered material at the surface of the Earth. And one time I was there and I said, okay, this is a 500 million year old weathered rock, kind of like a soil. And one of the students said, well, how come it doesn't look like soil today? And she was right, it looks so bleached. And it just dawned upon me that, well, of course it doesn't look like modern soil because there were no plants at the time. 500 million years ago, there were no land plants. And so this weathered material doesn't look like modern soil because it doesn't look dark and rich like modern soil. And that brings me to our final topic, where I'll talk briefly about colors. So here's one of the works of art in the exhibition. It's painted on something that's been called Belgian marble. It's not really a marble. It's a limestone that happens to be a very black, very dark limestone. And the cause of the dark color is organic material. So going back here, the reason why this weathered material doesn't look dark like modern soil is because it lacked the organic material that would have been provided by the dead plants. There were no plants at the time, no organic material, no dark color. But there are some limestones that have a lot of organic material, the organic remains of the critters that lived in the ocean. And if that organic material is preserved in the rock, it imparts this very deep black color to limestone. So perhaps the most common causes of color in many of the rocks you might see, or even soils that you might see, are listed here, something that you might want to know about. So often black colors are due to organic matter. The abundant carbon in organic matter imparts the very deep black color. And that's often the cause of black color in sedimentary rock and soils. In igneous rocks or metamorphic rocks, it's often magnetite. Magnetite is a type of iron oxide. It's the material you might find in black sands. If you walk at the beach or in a river, you'll see these stringers of black sand. That's often magnetite. So that can impart a black color as well. Yellows and reds, which is another very common color you'll see in many rocks, those are often due to hematite, which is another iron oxide that imparts the deep red, or limonite, which is sort of a wastebasket term for a mixture of iron oxide and oxides and hydroxides. And with limonite, you can get various shades of yellows, oranges, and reds. And that brings us to another work I'd like to bring up, shown in the lower right. It's a beautiful piece that you'll see in the exhibition shown here. It's in this freestanding display case. And they've done that because the piece is two-sided. So one side shows one painting, and if you walk to the other side, there's another painting. The lovely lady shown in the lower right is my mom. I took her there to see the exhibit. And she's holding her phone up to her ear because she's listening to the audio guide where I'm talking about this painting. So let's take a look at the two sides of the painting. It's painted on agate, this beautiful stone, beautiful rock with nice curvy layers that have different colors. And in this case, the agate has these different shades of colors, again, because of variable amounts of iron oxides and hydroxides. So agate is mainly silica, SiO2, which would be colorless, but because of these contaminants of iron oxides that come in as the silica is precipitating, forming the agate, then you can get these various shades of yellows, sort of browns and reds, which have been beautifully incorporated into these paintings, as you can see. Finally, I would be remiss if I didn't talk about the beautiful blue color in this wonderful painting that started the whole exhibition. This painting was acquired by the St. Louis Art Museum years ago. And Judy Mann, who really kickstarted this whole exhibition, this was the painting that inspired her to start researching this whole deal of painting on stone. And it's painted on this rock type called lapis lazuli. Let's zoom in on it and see what the minerals are like. So lapis lazuli is a rock, a stone, that consists primarily of three minerals. Calcite is the white material here. Calcite in its pure form is white, so that's what we see there. There's some pyrite. Pyrite is sometimes called fool's gold. It has a sort of yellowish golden color. But the majority of the rock is this brilliant, just fantastic blue. And that's a mineral you may not have heard about. It's a mineral called lazurite. And lazurite, its formula is shown here underlined in blue. It has sodium, calcium, silicon, aluminum, and oxygen, and sulfur. And sulfur is the element that is causing the color here. So there are many causes of color caused by various elements. I spend probably 2 weeks in my class in mineralogy just talking about color. But in many cases, the cause of color is due to electrons in the atoms jumping up and down or jumping across. And in this case, there's an electron that is jumping back and forth between sulfur atoms. And as that electron jumps back and forth, it absorbs the energy in light, taking away a lot of the colors of the rainbow that are not blue, leaving behind the blue to be the color that we see with our eyes. So just to wrap things up, as you can see, I could not have enough time to talk about all the rocks, the stones in the exhibition, but you can access this description of all the stones that I wrote up that's in the catalog. You can access them on your smartphone. So if you go to the Art Museum's website, slam.org, you'll hit the main exhibition page. And if you scroll down, as shown on the right, you'll eventually come to the section descriptions of stones. And there you can browse through the couple dozen rock types that are in the exhibition. So I think the take-home message that I want to leave you with is that rocks tell a story. Geologists are trained to read that story. That story is written in the textures, in the minerals, in the structures in the rock. And the exhibition Paintings on Stone is a wonderful exhibition where artists have taken the text preserved in the rock and integrated them and to complement their paintings. So with that, thank you again for showing up, for listening in. And I believe Jessica will take some questions.
Yes, thank you so much. That is absolutely fascinating. And we do have some questions, and I invite anyone, if you have questions, go ahead and type them in. I'm not sure we'll get to all of them, but we can try. Okay, so first question is, limestone is often thought of as soft and crumbly. What is the process that allows it to solidify and become suitable for use in art and construction?
Oh, great question. So many sedimentary rocks are loose and crumbly. You know, sandstone, loose sand becomes sandstone. Mud, which is very soft, becomes mudstone or shale. And the loose skeletal remains, hard parts of marine critters, that's loose material that eventually becomes rock. And that process is called lithification, turning into rock. And there are several processes that can do that, but two of the probably more important ones are compaction. Compaction, so if you take mud and you squeeze it, you compact it, you squeeze out the water, and a lot of the minerals there get pushed together making it more solid. In the case of limestones, another important process that turns it into rock is cementation. So you have these loose bits and pieces, and as waters percolate through that porous material, the water precipitates. Calcite in particular will crystallize between those grains, locking them together. A good analogy might be the salt in your salt shaker. It's supposed to be loose and crumbly, or sugar, but as moisture, gets into your salt shaker, it starts to dissolve some of that salt, and some of that salt recrystallizes between two grains, locking them together. So compaction and cementation, that's how you turn loose material into rock.
Yeah, okay, awesome. That is a great question. All right, someone else has asked, is the matrix of the porphyry always darker than the crystals?
Oh, great question. And the answer is no. Great question. So again, the matrix can have different colors. As we saw, the first porphyry was based on the purple color. I've seen porphyries that are jet black background, others that are really white. And again, the difference in color is due to often iron oxides, hydroxides, and other minerals or contaminants that might be in the matrix.
Okay, let's see. Someone's saying, thanks so much. This was a super interesting talk. They can't wait to see the show at SLAM, which is great. Someone would like to know, where might we get more info about the missing period? That was interesting.
Oh, wonderful. So that's referring to the Great Unconformity.
Mhm.
And that's a wonderful question, because everyone should be asking that, right? Like, what happened in this part of North America during the time that those rocks are missing? And a lot of that rock, we don't know how much, but some of that rock was eroded, deposited elsewhere. So there might be a record of that material elsewhere. One really interesting question that people have asked is, what caused this great unconformity? And that's an area of current research today. There are some papers that have come out just in the past few months. We don't have time to talk about that, but there's this wonderful idea that the great unconformity, at least in the US and other major parts of the world, might have been caused by glaciers at a time when the Earth was frozen over. It's called the snowball Earth hypothesis. Well, it's not really a hypothesis anymore. The theory of snowball Earth, where the Earth was so cold, covered in ice, and so a lot of the continents were being scoured out by continental glaciers, removing that record. So if that idea is correct, that answers your question. What was happening during that missing time was glaciers were doing their work, getting rid of the record.
Are there any places that you could send, folks who aren't, who this is an introduction perhaps to geology? Are there websites or books that you would point them in the direction of?
Another great question. I get this question a lot. They ask me, John, what book can I read to learn more about geology? And I hesitate to send them to a college textbook. There are several behind me, because the vast majority of college textbooks are not written for people who just want to learn a little bit more about the things they see. So if you wait a few years, I will get my book written.
Yay.
My mom is bugging me about this. She wants to read it. I'm planning to write a book, more coffee table type book that answers many of the common questions I get as a geologist, and not try to explain everything about the Earth.
Well, that's fantastic. What a great plug.
Give me maybe 4 years.
Okay,
I have other
right.
projects in the work, but
We'll be sure to check back with you. Let's see. All right, let's do a couple more here. Some rocks are highly porous, prone to fragmentation, or have colors altered by heat from cutting or polishing. Are any of the stones in the exhibition notable for the way that they were processed for use?
Oh, interesting. So I'm not sure what the questioner means by processed. So I suspect, and it's clear to me that many of the stones used in the exhibition were not that porous. So it wouldn't really make sense to use a very porous rock, because the paint would just sink in and it would be hard to work it. So many of the stones that have been used end up having a nice smooth surface after they were cut. And then if you purchase the catalog is this book that goes along with the exhibition. You can buy it in the bookstore, or the shop of the art museum. There's a nice chapter, which I have read, that talks about how the stones were prepared for painting. And if I remember correctly, many of the stones were just prepared like a canvas. They put a primary paint layer of paint, and then start painting on it.
So they actually clarified by saying by processed, I meant cutting, polishing, or resin stabilization, etc.
Okay, yeah. I'm not the best person to answer that, but again, that chapter talks about that. The rocks were initially cut usually with a wire. Many of these slabs were cut with a wire, often coated with corundum, an aluminum oxide as the abrasive, and it's like using a dental floss on your teeth. They're cutting through the rock, and that produces a nice smooth surface, which I guess they could try to polish some more using more of the abrasive to prep the surface.
Mm-hmm. Okay. Let's see. So we have a couple of folks asking just about the recording. So yes, we are recording this program, and it will be up on the museum's website within the next few weeks. We do have to make sure to close caption it. So I would say within the next 2 to 3 weeks, you can come back and look on the website, and actually on the page that John pointed out, the exhibition page. And all right, let's do one more question here. Sorry, we've got, someone has asked, what effect does global warming have on your work? And what are we seeing here, I guess, in Missouri?
On my work as a geologist?
Mm-hmm.
Yeah. So I am a so-called deep time geologist. I study fairly old rocks. So I don't deal with modern processes, except to help me understand ancient processes. But one aspect of global warming that I guess it's a two-sided sword. There are many places on Earth that are covered in glaciers, like Antarctica. I've worked a lot in Antarctica. I've done five field seasons in Antarctica. Greenland, that's covered in ice. And I know some of my colleagues who are somewhat excited that the glaciers there are melting. So a lot of rocks that were once covered in ice are slowly getting exposed. And that's, I guess, one way that my kind of work gets influenced by global warming. We're losing a lot of the ice cover. And I guess one benefit, if there's any benefit to that, is that a lot of the geology that has been inaccessible may soon be accessible, happily or sadly.
Right. Yeah, absolutely. All right, so we will close out with this question. Someone has asked, what drew you into this study? And then also, when did you start the study for the St. Louis Art Museum?
Okay, it's good. I'm glad person asked that question, because I neglected to mention at the very beginning that I initially wanted to be an artist. So entering college, as a kid, I loved to paint, I loved to sketch, and entering college, I wanted to enter into fine arts. My father put an end to that idea. And I said, I don't think that's a good idea. And I'm thankful for that in the end because I love being a geologist. So how did I become a geologist? I love being outdoors. I love to run. I love to hike, to swim. And so I wanted a field that would not keep me in the office. And among the fields, the few fields where you do a lot of work outdoors, doing field work, geology was one of them. And so that's how I became a geology major and continued with it as a career. For the interaction with the St. Louis Art Museum, the Judy Mann was looking for someone to collaborate with, a geologist who could help them identify the stones. And they contacted the St. Louis Science Center. I had done a lot of work with the St. Louis Science Center. I knew people there. I did this Science of National Parks program with Ron Giesler, who used to work there, and we'd take teachers out to visit national parks. So I knew people at the St. Louis Science Center. And so when Judy contacted them and she was asking them, do you have someone who can work with us, who's a geologist? Person there said, contact John Encarnacion at St. Louis University. And then I got the email. That's how it started.
Wonderful. Has it been far different than your typical work that you've been doing, would you say?
Very different. They use the word stone, not rock.
Confusing right away.
Right. No, but it's been a wonderful journey. I learned so much learning about all the different stones and rocks in the exhibition. I had to look up, it would be called something like Arno Line Jasper, which I had never heard of before, and I had to look that up. And oh, it's a limestone, is what it is. It's not even a jasper, Arno Line Jasper. Fantastic stuff.
Just
So,
lots of fancy
and again,
words.
most of this is written up in that the descriptions of the stones that people can access on their smartphone.
Wonderful. Well, thank you so much, Sean. This has been fantastic. I know lots of folks here will be looking out for that book, and we just all really appreciate your perspective here. I did also, if those who are watching have not been able to see the show, either you're not in St. Louis or haven't been able to make it in, I do encourage you to come if you're here, but if you're not, we do actually have a virtual tour of this exhibition. And so I've just dropped that link into the chat if anyone would like to go there. Of course, that can also be found on the exhibition website, which John mentioned earlier. So go ahead and look there. And the audio guide that John is on is also there. So please check that out, even if you aren't able to come and see the actual show in person. Also, if you'd like, please join us next Thursday, April 28th at noon to hear curatorial research assistant Abigail Yoder discuss the 19th century symbolist art movement, in which artists responded to the rapid modernization by looking inward instead of outward like their contemporaries who were painting in the Impressionist style. So with that, I encourage everyone to go register for that and have a great Happy Earth Day. Thanks, John.
Happy Earth Day.